So next up, we've got Cassandra Perryman. Her talk is on statistics for the skeptical researcher. So welcome, Cassandra.
Mine doesn't look quite as neat as that. We'll see. While Hilton's getting it loaded, I will say yes, the nasty word of statistics has been dropped, so I do apologize for that. I promise to be as friendly and speak in English as much as humanly possible. I am going to try to give you the best overview I can without actually teaching you statistics, which is actually the zone I'm more comfortable in, but anyhow. So again, while he's getting it going, my name is Cassandra. I am a PhD candidate at the University of Queensland. Yes, I'm a bit old to be a PhD candidate, forgive me. My specialty is statistics, psychometrics, and data science. Goodness knows I've been in the field for, well, longer than I should admit. Today I'm just gonna start out with taking you on a bit of a journey. As many of us do, we debate online, yes? Okay, so imagine you're in this great, impassioned digital debate with an anti-GMO. Okay, those happen, right? You tell them you want evidence, that good word we love to use, thinking they'll never come back with anything, right? And sure as the day is long, they come back with a study. Not just any study, the best Mercola has to offer. Straight off the Natural News Network, right? Hot off those digital presses. Well, you got a problem here. One, they've actually provided you with something, right? When does that actually happen? So you know it's going to be crap. You know it. But if you readily dismiss it, you're creating a genesis fallacy, right? Just because it came from Natural News Network, it must be crap, right? Logical fallacy. If you don't at least read the study and the debate continues, you risk not understanding the point they're trying to make. You've now committed a straw man fallacy. And we know that anybody on the other side loves to call us out on logical fallacies, right? It's what they do. They go, oh, you committed it, so now you're all wrong. Well, let's talk about what you do then when you get this study, what you look at, and how you can debunk it, okay? So we're going to look at an example of a randomly controlled trial. So of all the things in statistics, I picked the RCT because that's the woo provider's favorites, okay? Fluoridation, medical devices, homeopathy, vaccines, GMOs. They're all going to throw you things that say RCT. Why? Because it's the gold standard of research. It's what real researchers look to achieve as well. So of course that's what is going to be mimicked. So it's based in statistics, hence we have to go back and say, look, it's statistics. So what is statistics? It's the science of taking data to extrapolate a picture. That's it. Numbers come in, and we hope numbers with some sort of meaning come back out the other side. This isn't ideas and concepts that go in, okay, as opposed to some other sorts of thing. This is numbers in, numbers out. So we're going back to our example, Natural News Network. Here you go. Now this is a free access journal. I realize it's already been ripped to pieces. I figure since it's already been ripped, it's going to be a fair enough one to show you what's been done to pull it apart. So you can obtain this from GMO Judy Carmen. They love the great terms like long-term and toxicology. So keep those in mind, long-term and toxicology, and this is supposed to be an RCT. So we get our title, we go straight down to the abstract. Okay, now I went ahead and highlighted the pieces that are going to be important pulled out of this, but the whole thing's up there if you want to peek through it. Okay, so the abstract is your place to start. You want to do a quick scan, this is a scan and pick up the relevant details. It's hard because I'm used to being up there, so you're going to see me point a lot. You want to know how many subjects were in the trial. Okay. You want to know what groups they were in, and even though her title doesn't say RCT, you can tell she's going for the RCT when it says, we randomized and fed. Ooh, randomized, right? That's the words you want to see. Now, in this one, I want you to kind of look at the bottom two here, and it says GM-fed pigs had uteri that were 25% heavier than non-GM-fed pigs. Probability 0.025. Just keep that in the back of your head, because that sounds impressive, doesn't it? Like, ooh, that's bad. Bad for female pigs. Bad for females, right? It'll make your uterus bigger. Not good. All right, so just keep that one in the back. Come on, uterus, that's a good word. That's why I picked that one. So next, we're going to skip to the bottom of the introduction. Yes, I'm saying skip to the bottom. Don't read the intro. Their basic logic is their basic logic. It's fine. If you have nothing better to do, go ahead and read it. What's going to be important, though, isn't the logic that they've built on. Shaky or strong, doesn't matter. It's going to be what they actually did. Okay? You don't debunk a study based on the work before that study. You debunk the study based on the study. So we're going to jump down to the hypothesis. Okay? And you can see it here. The aim of the present study was to perform a thorough, long-term toxicology. Toxicology was their focus. Okay, and it's 22.7 weeks. They've randomized them to feed them GM soy and GM corn diet, or an equivalent with non-GM ingredients. Okay, that's a hypothesis. Now, here's the problem. That's extremely vague. What are they doing? What is their goal? This is an exploratory hypothesis put onto a randomly controlled trial. Okay? Now, not all exploratory hypotheses are bad. Sometimes exploratory is exploratory. Randomly controlled trials are not exploratory. This should be your first kind of red herring. Okay? This is the first bit that something is going to go wrong. This is far too broad, far too vague. Okay, so right off of the hypothesis, we go into the methods. RCT, right? We're looking for randomization, control, randomly controlled, and we're looking for something called quantification. Okay, quantification is very important in all research. Okay, so first, randomization. This is a quasi-randomized study. Now, what do I mean by quasi? They didn't go around to a bunch of farms and say, hey, can we have 2 pigs from your farm? Any 2 pigs from your farm. They must be about this age or about this weight, so we can add them to our study. Instead, they took 1 farm, okay, got a bunch of pigs, and after they were weaned, put them in 2 separate pens. Does that make sense? Now, that kind of matches reality, because when doctors are testing medications, you can't just pick 30 people off the street and say, hey, try this pill. There's a problem with that. What if they don't need that pill? What if that's something to treat cancer and now you're giving it to healthy cells? So that is the reality of randomization, but in this case, we're looking at pigs. Pigs on farms just need to eat. It doesn't matter where the pigs came from. Okay, so that's another clue that, okay, why were they picked from that farm? Okay, so next we have control. There's only one thing in this study that you really have to control, and that's food. Right? They're talking about GM feed or non-GM feed, and what does it say? Pigs were on a self-feeding full feed basis. Every pig could eat as much as they wanted, whenever they wanted. So now we have a pig who eats a lot, we have a pig who eats a little. We have a pig who doesn't eat. We have a pig who really likes what's at the bottom of the trough and might have gone bad. We have a pig who really likes the stuff that's at the top of the trough and won't have gone bad. We don't know how often they were fed. We don't know how often the trough was cleaned. We don't know any of this, okay? So this kind of goes more into state. Here's where just knowing a little bit can be very dangerous. That second little bit talks about mycotoxins. That's mold on food. Now they do something a bit tricky here, and they say that the levels are well below the USA and EU limits. Unfortunately, those limits are very high. All said and done, though, the feeds are not the same. So they have not controlled the food. Okay, so the last little bit that I talked about is quantification. Now, quantification is just as important as randomizing and control. Quantification is the process of defining your variables. Okay? So we're going to do a little subset imagine here, defining a variable. How much do you have to define that variable? We have two beautiful little girls sitting here in the front that make a perfect example for this. So if you imagine you're a mom or a dad or a partner, and you say, I need the dishwasher loaded. And they say, well, I don't know what that means. I thought I did it. Anybody with kids goes, yep. So you need to quantify loading the dishwasher. Every parent's done this. You're going to say, the dishes that go from the edge of the stove all the way across the counter through into the sink. I have 3 sons. Those need to be placed from there into this device here known as the dishwasher. Crazy device, this. Plates need to go on the bottom shelf in a vertical fashion. Silverware needs to go into the silverware caddy, which is in the center front of this bottom tray. Anything pointy, facing down. How many times have I done that? Okay. Then once we've gotten rid of the plate and the silverware, we open the top tray. We look at the bowls and the glasses. Now, bowls and glasses have a concave section in them. Concave faces down, glasses in a vertical fashion, bowls at a 45-degree angle in the center rack. Can the kid then say, I don't get what you want me to do? Well, they can, but they're not going to get away with it anymore. That is quantification. Now imagine what my poor children go through. Oh, but Mom, I got a B, but was that B? Anyway, so I'm just going to pick one example of quantification here. Their method section actually goes on for 2.5 pages. 2.5 pages. Let me just tell you, as a researcher, there is no reason on the face of this earth I want to write 2.5 pages of absolute crap methods. It is shocking how much time this must have taken. Okay, so this one is how they've operationalized stomach inflation. Now, something to note, and I'm actually going to come up here. Okay, they say that earlier they'd done another preliminary study on pig stomachs. Okay, so some other study is how they determined aspects of these pig stomachs. But they don't attach or refer to that study, do they? There's nothing there. And those pig stomachs were obtained from a random sample of pigs from the same abattoir and some other ones. So we don't know where those pigs came from. We don't know how those pigs were raised. We know nothing about the pigs that set the norm for this population. We don't know what they picked. So then they go on to say, based on that, we have nil, mild, moderate, or severe. Okay, we got 4 categories. Think of the dishwasher now. Typical examples, each of the 4 categories are here. Can you tell me what they saw in the nil, what they saw in the moderate, saw in the severe? Have they defined that variable at all? Or does it just look like, hey, we got some guy and he did some things? Well, yeah, they got some guy and he definitely did some things. Okay, so quantification, we've got 3 X's now. I guess the study's out. No, we'll go on. Okay, so after methods, we get into the analysis. Now, most studies are going to tell you the packages that they analyzed with. That's great and good. Most of the time, you're going to see SPSS. I say because it's the stupid proof program. You click. It's a bunch of buttons. We could teach it to any of you in a couple of minutes, but it's a highly powerful program. So that's what's used frequently. They give you a bunch of really fancy things in. Interquartile range. Ooh, they clicked more buttons. Wow. They clicked a lot of buttons. You're not supposed to do this, by the way. This is a lot of button clicking. Not good. Okay, so data were tested for normal distribution. That good old bell curve. Come on, we're skeptics. We know what the bell curve is. Data source Rex. Come on. Okay, so they did the Shapiro-Wilk test. All that tells you is if data sitting way to one side or way to another. Fancy name, easy task. It's called skew. If a normal distribution was found, data are expressed as means and standard deviations because they have to be. That's how you do it. And then they use a parametric method, normal data, bell curve t-test. Okay, they go on to say all these other ones they do, categorical, blah, 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 blah. All it basically comes down to is a different type of t-test. They did t-test, 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 and t-test. That's it. Let me just state right now, if you see randomly controlled and then it says t-test, you can launch it. Okay, at that point, you are all right to go on with a confirmation bias. You are free to continue ripping it to pieces. Don't use a t-test for an RCT. Okay, so what else could they have used? And I'm just gonna do a little bit of a statistics overview just to give you a bit more tools in your toolbox. Okay, something to note about t-tests: they are not causal. T-tests are not causal. Eyebrows go, huh? But they're using a t-test, and they're saying that food caused. T-tests are not causal. All a t-test tells you is that there is a difference between the mean or average of two groups. That's it. They're different. T-tests are based on means or average and standard deviations. That's just if you try to put a line through the data, how much they vary from that line. Okay? Grossly simplified, but still. Okay, so how do we start blatantly or brazenly getting into causal? Well, causal, ANOVA is a complicated set of t-tests, but it gets a bit closer to causal. It has a bit more controls. It allows for covariates. It allows for a lot of other things. It gets you closer, but it's not causal. It's not causal. So if you see T, and the things in the parentheses are how they're reported. So if you flip to the results and you just look for a little cursive or italic number or italic letter, you're going to know what they've done. T, F, and R are going to be your most common. R is called a Pearson's correlation. Well, correlation is not causation. That's it. But people love inferring causation off of correlation. And the next thing you're going to see a lot is significance probability. Just like at the beginning, 0.026. Ooh, right? That's really good, right? All significance probability is the 95% certainty, 95% certainty that we didn't screw it up. That this result was not just a product of random chance. So we're 95% certain this didn't happen just because of random chance. That still leaves 5%. Okay? Then you've got the people who drop it down to a 0.10. That leaves 10%. 10% of it was random chance. So really, statistics does not ever reach 100%. There is no certainty in statistics. As I get to tell my students all the time, I'm so sorry, but if you get 100%, you failed. A couple of you will get that. The rest of you are like, really? The good researchers, too, will also report effect size. How strong is the actual relationship between the two variables? How not just how certain are we, but how much do they actually overlap? So you'll see these great results. And, probability of 0.001, and look at how powerful it is. The effect size is 2%. So they only overlap by 2%, but you're saying this is powerful? You've got a problem here. And depending on the test used, they're Cohen's D. So it'll be a D, a W, or an F is your effect size. And most folks will also put the word effect size in there for you. So now going back, we skip straight to the tables. Yes, straight to the tables. If there are tables, don't worry about the words. Isn't that great? I teach statistics and I'm telling you, if there's tables, don't worry about the words. Here's the problem. Which table? Okay, we've got 2, 3, 4, 5, 6. We have glucose, kidney, uterus, heart, cholesterol. Do we have any toxins? We have nothing that is toxicology in our results. So our title's just gone out anyway. Our hypothesis has just gone out the door. And we've got what's called shotgunning. Okay, some people also call it data mining. It's the basic idea that you grab a shotgun and you shoot at the side of a barn. Okay, boosh, big cluster pattern. Then you run over with a can of paint and you paint the target. That's what they've done. They've tested everything they could get their hands on and said, hey, look, that one's different. Look, but that's different. Okay, so we're going to go back and look at a specific one. I love this. Is it a uteri or is it uteruses? Is it the Greek or the Latin? Is it octopi or octopuses? I don't know. Okay, so at this point, they've ignored their hypothesis. They've ignored their title, which to me takes a lot of effort. When you have a title that straightforward and then you ignore it, we have a serious problem. Okay. I'm going to go back to pointing. I'm a hands-on person. So we have a couple of clues here that are bad, and I know it's a bit hard to read. We have things that are ignored because they're contrary to the hypothesis. With the stomach, this mild inflammation and no inflammation, there's more with no to mild inflammation in the GM group. They did better, but they go, oh wait, it's the severe. There's more in the severe group, see? That's a problem. The second you see that, you have confirmed data mining. They're ignoring anything that is opposite. Okay, so now we're going to go back to this whole uterus thing. We look in the non-GMO fed, we look at the uterus, and they've got a what here? A 0. What do they have in the GM fed? I don't know if you can read it. A 2. A 2. So wait, at the beginning, they told us they had a sample of 168. They told us that the GM fed had this massive, swelling of the uterus that was 25% times bigger, and their sample size was 2. It was 2. So I tell you what, when they're also going by whether or not it was filled with fluid or not, so they turn this into a dichotomous variable, yes or no. Yes or no. 0 yeses, 2 yeses. There's a statistical difference there. We got 0 and we got 2 when we only have yes or no. It means nothing. That 0.026 means nothing. Look around. If nobody raised their hand, and then I said, okay, well, who has a dog named Boo, and 2 people raised their hand, 2 is significantly different than all the people who don't. That's it. That's all they've done. Okay, so it's a good sign there's a problem. Now, even further, we get into another problem here. We have our sample size, and over on the right-hand side, it says 73 and 72, correct? They're talking about weighing the organs of 73 and 72. What does it say here? The autopsy results are based on 33 and 37. Where did 40 pigs in each group go? Schrodinger's farm. I'm sure if you open a door somewhere, 40 pigs are going to fall out. Okay, so I'm not going to kick a dead horse here. Dead pig. I think you get kind of the basic point, and hopefully a very basic overview, and hopefully I've caught us a bit more up on time. So a couple of things to kind of walk away with. One, even if the research coming at you is going to be bunk, it is your responsibility to read it. It really is. We want to ask for evidence. You need to accept the evidence, in your hands, not accept. Okay? You need to read it. You need to understand what you're looking at when you read it, so that you can go back and debunk what has been handed to you specifically. This keeps the argument on task and in line. Linear arguments make sense, right? Circular nuh-uhs get us nowhere. Keep it linear, okay? In order to keep it linear, you need to understand how to read and look at this research. Skip to the end of the introduction. Quickly, briefly check through their methods. Check to make sure controls are in place. Check to make sure things are quantified. But don't be afraid to look at the results. Understand T and F. Okay, I saw T, they said causal, this is no good. And that's the basis. Look, they used a t-test. A t-test is not a causal test, therefore assuming any causality is not ethical. Done. Done. How does somebody come back after that? This isn't ethical, that isn't causality. But it says, no it doesn't. It says T, okay? Get to know these basic little things. You don't have to really understand how the t-test was done, but I could torture you with that. But just be wary too when reading research that statistics can be bent, they can be manipulated, data can be trimmed. 37 autopsies suddenly became 73 autopsies in the table. That's a problem. Okay, so data can be trimmed, manipulated, moved, and nothing in statistics comes with 100% certainty. Okay, so the big thing is when you get these, learn how not to be fooled, and learn when to change your mind. You never know. If you know enough about the stats and a paper comes after you, you can look and realize that it's good. Maybe this is something we should look into more. Maybe somewhere along the line we were wrong. And that's the joy of knowing statistics. But in the end, the important thing to remember is that correlation does not mean causation. Because goodness, that's at a 0.94. Think of it on a scale of 0 to 1, my friends. 94% overlap between per capita consumption of cheese in the US and the number of people who died by becoming tangled in their bed sheets. So, and that's it. Are there any questions? Look at you're all like stats. So, don't ask her nothing.
All right, thank you. How good was that?
I tried.
Even good science or good journals publish articles where these kind of things come into effect too. So just because you believe or you think it's a good science doesn't mean that this isn't actually applicable still. So it's very good information to take into account.